All right, good afternoon, gentlemen. I just wanted to take the time to apologize that I felt like my first lecture wasn't as effective for you and kind of probably left you with a lot of questions. And so I'm taking this time to record and like redo my first lecture because I felt like I could do it better and more effective for you. And so, as a reminder, again, we're hybrid. And so if you are watching this and it is on the white cohort day and you are 100% virtual, you should be viewing this. Um, you already viewed this, and so you should be doing the lab. However, if you came back and you're from the white cohort when you were online or you were 100% virtual, I want to say hi. I'm happy to have you here. I hope that this helps you a lot more than my first one because I think that this will be a lot more effective. So the plan today is I'm going to go over measurement again, and then you have a worksheet that you have to turn in, and you need to finish it and get it in as soon as possible. You have a week to complete it. However, you should be able to successfully complete this with ease. So yeah. So to take notes in chemistry, remember, and physics, so physical science, remember, I do need you to have a paper copy of all your notes because I will be doing periodic notebook checks, and one might be coming up here shortly. So it's in your best interest to take your notes in your notebook. When you're taking notes, I do ask that you always have your header with your date, the unit we're covering, and the topic title. Today's the 27th, so you should be checking the date, record it as 8, 26, 27, 28, will be like 31, and make sure you have unit 1, and we're taking notes over measurement in science. Measurements in science vary from a couple different things. So you can measure the length of an item, you can measure the mass of an item, and you can measure the volume of the item. So a couple different ways that you do that is you use different instrumentations to get that measurement. However, it's always important that you note that when you are measuring in science, you're also using different units than those that we typically use, especially as Americans. In science, we use the metric system. And so when we're measuring volume, we use milliliters. And when we measure mass, we use it on our mass balance, we measure grams. And length is always measured in centimeters. I do have this handy table for you, so please copy that down if you have not already. The more precise the tool that you use, the better measurement you have. And so the tool that we use gives us these units, but using the correct tool will also give you a precise measurement. For example, when you're measuring volume, you use a graduated cylinder because of how close the ticks are, and that you can get a better estimated number because you can go to at least one decimal place. However, I would not want to measure volume with a beaker if it's something that's extremely important in lab. You can measure volume with a beaker if you just need 20 milliliters of water. However, if I need an exact measurement, I do want to use a graduated cylinder in place of a beaker for that example. If you have not copied this down, pause the video at this point. Make sure you have this table down because, again, this might show up on a quiz next week. So, now I want you to take the time and I want you to measure this line segment. So pause this video and measure the line segment to the best of your ability. It might be a little bit difficult because when I look at this, I could say, oh, well, it looks like maybe 3 1/4. That's my best guess because I really don't have any indication of what the measurement in between my 3 and my 3 1/2 actually is. So if I take this line measurement, I'm going to make my guess maybe like 3 1/4, so 3.25. So write that down and make sure you have your units. Now, measure with this ruler. And so pause this and measure what you get. So when I look at that, I think about more like a 3.23 cm. And so the top one indicates what I thought it was when I didn't have my ticks, but with the addition of my ticks, I can make a better rough estimated guess to do maybe 3.23 centimeters. The difference between these is that I have those ticks that give me a notification of what the in between my 3 and my 3.5 mark looks like, so I can have a better estimated value. It gives me a better estimated measurement as well. So the adjustments that I made is that now I was able to use a piece of paper or something that notifies me of, hey, this is kind of the closest it's at, and I can make adjustments on how I see the ticks in between my 0.1 values. And it affects my result because it makes it more accurate because I'm able to have a better and more focused estimate. As you recall, for the blue cohort specifically, we talked about an estimated or an uncertain digit. The final digit of a measurement done in the lab is your estimated digit. And so make sure that you have this down. It's very important. When you're doing with your estimated or your uncertain digit, it's always going to be one decimal place past the smallest division on the measuring device that you see. And so because you're estimating it, the value is uncertain. So much like, which I'm going to backtrack here. If you need to take these notes, just pause this lecture. I'm going to go back. So for example, when I was dealing with this ruler, I didn't have any measurements between. And so I could make a guess and say, oh, I think it's 3.25 because that's what my estimate was. I viewed it as halfway between 3 and 3.5, but I could not give a better estimate other than 3.25. So one decimal place would have been fine because I could say 3.5. So I could have been like, 3.2. Yeah, 3.2. So my 0.2, so like in this case, I would say 3.2 centimeters, and that's like a rough estimate. Oh goodness, there we go. My 2 would roughly be my estimated value. And that's because I could tell you for a fact, hey, I know it's 3 centimeters at least, but I know it's less than 3.5 centimeters. And so I made an estimate and I said 0.2 as my estimate. But if I went with this ruler, I could tell you I have a better estimate for it. So I could say, hey, I know it's 3 centimeters and I know it's where the 0.2 is. Now I can add another decimal and make another decimal, an estimated value based on that. So instead of having 3.2 as my estimate with my estimated value being 2, I can add a second decimal and that would become my new estimated value because I can now kind of think about where you have your ticks and you have your big tick. I can look in between these ticks and see 10 little small ticks in there. So I can make an estimate based on those 10 little small ticks. So it's kind of like enhancing. So with my 3, I can have, one decimal place if I have my 3 and then like a 0.5 there. I can have one decimal place. But the addition of these other ticks gives me 2 decimal places. So that's how I can calculate where my my estimated value is. Now, this is extremely important for you to know because in labs, you will be asked to underline estimated values for this unit. And so you need to understand how and how far that you need to estimate your value and the way that you can tell that on the device. Now, measuring volume. There are 2 ways to measure volume. You can measure volume in a beaker or a cylinder. In the beaker, when you measure volume, you're going to look along this line. And measuring volume, you're always going to be able to have like no decimals specifically because here's my 40 and here's my 50. I have 10 ticks in between there, but all I can really estimate is maybe 48. And my 8 would be my estimated value because I can't tell further than that if there's any additional ticks in between my 8 and 9. If I wanted a more accurate measure with volume, I would use a graduated cylinder. When I measure with my graduated cylinder, I'm going to measure this part, which is called the meniscus, which is spelled, I think that's it, like this. If I'm wrong, I will correct myself. The meniscus is where that dip in the water happens, and the reason because of that is when the water's in the graduated cylinder, it hugs to the side. And so if you're measuring on the outside, you're adding additional volume that isn't there. And so measuring at the meniscus is giving you an accurate representation of that volume. And so when I look at this, I know here I have 1, 2, 3, 4 that I'm going up, and then I have 10 little ticks in between these. But when I look at this, I can say, hey, it's above 20, it's less than 25, it's 24, and where does it fall between 24 and 25? In this case, I believe it's right on the line, and so my estimated value would be 0 because I don't see it above or below that line. When you're reading volume, you always want to hold a sheet of white paper behind the instrument you're using, so in this case the graduated cylinder, to help you line up your eyes with it. When you get down to measure, always measure at eye level and never hold your sample. You always want to have it on a flat surface like your lab bench, and you'll always count up. You'll be practicing this in lab, and so it's important you have a really good understanding on how to read it. Here's our checkpoint, so we're going to kind of check mark and see how we're doing. I want you to measure this line segment, pause this video, and then we'll discuss shortly. All right. So when I make my estimate, I always do where I say, okay, I know it's more than 4. I can do at least 2 decimal places because I have my little ticks here. So what I do is I go, okay, it's more than 4, less than 4.5, so it's going to be 4. Now I need to find where it goes, and I see it as at least I'm past 1, but I don't pass 2, so I at least know it's 4.1. My next step is saying, where do I think it lands? In this case, I think in the middle of 0.1 and 0.2, so my 5 would be my estimated value. Next, we're going to measure the volume. Specifically for this one, I want us to measure the second one and the fourth one. The first and the third, you can practice on your own. So when I look at number 2, specifically, I want to go start and I want to look at the meniscus here. So I look at the meniscus and I find where it's at. I see that this is going up by 1s. And so my next step is I go, okay, so it's 15, 16, 17, and here's 18. However, when I bring my line over, I kind of see that it's a little lower than 18. So I look at that and I go, okay, well, I can go at least 0.1 decimal places. And so I say 17.9 milliliters, where my 0.9 is my estimate. If you saw it at 18, you would write 18.0, and the 0.0 would be your estimate. Now looking at number 4, it's a little bit more difficult to tell because it's moving by 5s. And so here's 75, 70, 80, or 80, 85, 90, 95, 100. And so right here I'm at 90, and I see that is at 90 pretty much. And so my estimate would be at 90.0 milliliters, where the 0.0, is that estimated value. However, you don't really need to have the 0.0. The 90 that you have could be your estimated value. because instead of having 10 little ticks in between, we're only having 5. And so it's harder to determine a decimal in that situation. And so you could stop and say, oh, I think it's at 90. And your 0 would be your estimated value, and that'd be completely acceptable. All right, when we're measuring mass with balances, we need to understand which the estimated value is on that balance. And so based on our discussion earlier, which number represented is the estimated number. In this case, our estimated number would be the 7. And the reason why is when we're on a balance, it can tell me definitively 2.8 is the mass. But it takes that second decimal and it's trying to figure out the best way. And so when you're working with a balance, you might notice it always teeters kind of on the last digit. And that's because that is the estimated value for your balance. When you're measuring temperature, you always want to make a rough estimate as well. And because they're the ticks of 1, you can at least always go 1 decimal place over. And so in this case, what is the estimated number for this thermometer in your opinion? It might be difficult to see, but when I look at that, I see about 62.8, 62.7. And the reason why is I usually take a piece of paper and put it over, and it's not surpassing 3. However, it's pretty close, but there's still enough space that I can at least do 0.8. So my best guess would be I go up 1, 2, and I say 62.8, where the 0.8 for my degrees Celsius is my estimated value. When you're with a thermometer, you always want to make sure that your thermometer is not touching the inside of the glass. And so when I say this, you want to always kind of center it in the middle and then wait for it to kind of settle on the temperature it's at, because it will affect the temperature that you overall get. And when you are done using a thermometer, you always want to store it upright. You never want to lay it down. Next, we're going to move on is a percent error, which is calculating accuracy. This is used when you calculate a value in the lab and you're given an actual value that might be calculated with the use of technology or with a very, very, very accurate instrument. So an example of that is in the lab, you calculated the value of your beaker, let's say, and you are like, hey, the volume in this is this much. But I come back and say, actually, it's maybe a completely different number. So you get a chance to see, oh, how close was I? And calculate that percent error. So we're going to do this with an example. So first things first, make sure you have your notebook. Okay. In the lab, you calculate the density of a liquid to be 1.24 grams over milliliters. The actual value is 1.30 grams over milliliters. What is the percent error? Right away, I like to pick out what my information is telling me. So I want to find my calculated value. So when I read through the problem, I say, okay, in the lab, you calculate the density. So the calculated value that I found was 1.24 grams per milliliter. So I write that down. Now I want to find my actual value. The actual value is given to me in the second bullet point. It says 1.30 grams per milliliters. So I'm going to write that down in my actual value places. And I multiply it by 100. Now my next step is to do my basic algebra skills. I'm going to look at my parentheses and see what's there. First things first, at the top of my fraction, I have to do the subtraction. So I plug it in my calculator, and I get negative 0.06 grams per milliliters. Once I've done the subtraction, I'm now going to take this value and divide it by 1.30. I'm going to get a long decimal. Make sure that you write the entirety of that decimal and keep it in your calculator until the end of all your calculations before you round. So I get negative 0.046153846. And I wrote that out. Again, pause this if you need to copy it out or just rewind so you can listen to me say it. And my next step is I'm going to multiply that by 100 to get my percent. Now I can round. So I look at my value and I see negative 4.615. Because my third decimal is a 5, I can round up to make my answer negative 4.62%. And that is calculating percent error. So now that we had some time, I want you, we're gonna go over how to determine the values, and then you'll practice some. So there are two types of error that you can have, is you can have a positive percent error or a negative percent error. Your positive percent error is your overestimated value. It means you had too much of something, or you over did the measurement. You just had too much, because when I do subtraction on the top, if I have a big number and I'm minusing it from a small number, I'm gonna have a positive number out of it. And so I'll have a positive percent because I had too much. If I have a negative percent error, I underestimated. So for example, in this problem, I calculated 1.24, but the real value was 1.30. I calculated less than what the actual value was. So I took a small number and I subtracted it from a big number. That means I would end up with a negative value on top. So I have a negative percent because I didn't have enough. So positive is too much and negative is not enough. Now that we've gone over that, let's practice a little. So pause this video and you take a minute and you actually work through it, and then we'll work through it together. It reads, a student measures that a piece of string is 2.6 centimeters, but the actual length of the string is 2.9 centimeters. What is the student's percent error? So take a second to solve it. I'm going to set it up. Okay, so right away, a student measures. So they measured this amount, which means it was calculated in the lab. So our 2.6 is our calculated value. Our actual length, which we can sell right here, is 2.9 centimeters. So, sorry, my hundred's on the side. When I set it up where 2.6 cm minus 2.9 cm over 2.9 cm times 100. My first step is I'll take 2.6 and I'll subtract it from 2.9. I'm going to end up with a negative number. I take negative 0.3 and I divide it by 2.9 centimeters to give me negative 0.103448276. Here is that decimal if you did not hear me. And then I will take that number and I will multiply it by 100 to get my percent. Again, I can round to two decimal places now. So I end up with negative 10.34%. I have one more problem for you to go through. It reads, a standard mass of 100 grams was placed on a balance. The balance indicated that the mass was 101.6 grams. What is the percent error for the balance? So take a moment to complete this on your own. I'm going to set it up. This might be a little hard to tell. However, a standard mass of 100 grams was placed on a balance. So a standard mass is the actual mass. So here's our 100 grams, which represents our actual. The calculated was the balance. So we want to find, this is our calculated, and we want to know how bad or how off the balance was. So when we're setting it up, 101.6 grams is our calculated, and our hundreds are our actual because it's our standard. And we're going to multiply it by 100. Our first step will be to take 101.6 minus 100. You end up with 1.6 grams. After I do that, I'm going to divide 1.6 grams by 100, which you should know what's going to happen. So I end up with 0.016 times 100. So it looks like this. I multiply 100, and I get the percent of 1.6. So I end up with 1.6% as my final answer. That is all the information I have for you. As a reminder, you do have a homework assignment, the Making Measurements worksheet. When you complete that, you do not have to do number 6, and so cross out number 6 on our Making Measurements worksheet, and make sure you turn that lab in the next time I see you in person. If you have any questions, email me. But until then, have a wonderful day. Bye.